So in our first example for uniformed acceleration, we have an object initially traveling at a velocity of 2 meters per second north accelerates uniformly to a velocity of 9 meters per second north in a time of 1.5 seconds. Calculate the displacement of this object during this time. So first and foremost, what we want to do is we want to find out what we have and what we're looking for. So first thing we're doing, what are we looking for? So calculate the displacement of this object during this time. So we're looking for our displacement, which is d. Then let's go through the problem again, make sure we write down all our variables to see what we have. So an object initially traveling at a velocity of 2 meters per second. So keywords initially and at 2 meters per second. So that's our v1. North, in this example, it just states that it's going north and velocity 2 is also going north. That is irrelevant in this problem. It just says that it's going in the same direction. In other problems, it would be very consequential. If we go north and south and east and west, you get more confusing. But in this example, it's very straightforward. It's literally straightforward. So then we got uniformly to a velocity of 9 meters per second. So that's our v2. In a time of 1.5 seconds. So there's your time is 1.5 seconds. Now, we figured out what we have and what we're looking for. So now, in the previous video, I gave you this table. In this table, in the previous video, I had made a mistake, in case you copied it down. For this equation, it's a plus v2 plus v1, not v2 minus v1. That was my error. So now what we're going to do is we're going to look at what we got and what we're missing. So we're looking for d, but we don't have acceleration in this problem. So if we look at the top here, we look for acceleration, we say, okay, this one does not have acceleration. It has v1, v2, d, and t. This is the equation that we need. All right, so let's start filling that in. So d is equal to v2 plus v1 over 2 times time. All right, let's start filling in the equation. So d equals, this is the way I like to do my math. I like to switch out the brackets for bigger brackets and put the small parentheses in for variables that I'm finding the answer for. I realize there's a shadow on my screen and I apologize for that. Okay, v2 is 9.0 meters per second. Do not forget your units, very important, plus 2 meters per second. I didn't put the 0.0, that's irrelevant because it's 0. Over 2 multiplied by time, which is 1.5 seconds. All right, so we'll make this easy and we'll go one step at a time. So if you remember your PEDMOS, your BEDMIS, I believe that's what it's called in English. Sorry, I did my math in French. So we have brackets first, right? And then we do multiplications. But here we have a divisional sign. So basically, you have another bracket right here. So we got to do this addition first. So we have 9 plus 2 is equal to 11.0 meters per second. Now, it's more of an algebra thing, but I'll get to it right now real quick. You got to make sure you keep your variables, your units. It's very important. If, in this specific example, you cannot add things that do not have the same units. It does not work. So because these are the same units, you can add them together. Alrighty, 11 over 2 times 1.5 seconds. All right, so now we continue with our BEDMIS, and we got to do brackets again. So 11 divided by 2 is 5.5 meters per second times 1.5 seconds. All right, so now I could explain to you where your seconds go in another, it's a math problem or algebra. but basically this ends up looking like over second times second. So what ends up happening is these cancel out. Reason being is that it's basically like saying 1 over 1, and this becomes 1, and so you go m times 1 is m. So that's how you get your meters. So D equals, we do that, and it's 8.25 meters. So in this problem, we use not scientific notation, it's significant digits, I believe is the term. So what we want to do is you basically look at what is the most precise decimal place in your problem. And so in our problem, our least precise. So our least precise is 1 decimal place. So our answer can't have 2 decimal places because that's too accurate. Basically, our instruments aren't accurate enough to say that this is how accurate it is. So we have to actually bring that to 2 significant digits. So this answer will become 8.3 meters. There's a scientific rule that explains that if you have a 5 at the end, I don't remember it, I'd have to look it up, but basically you either round up or round down. But if it's a 5, I believe, well, in this example we round it up, but it's something along the lines that you want to try to keep either, I think it's an odd number. So if it was 2.5, you go up to 3, but if it was 3.5, you'd go down to 3. Again, that's a different explanation for another day. But here is your answer for this problem. Pretty straightforward, and not too much going down. All you got to do is use your tables, and physics is relatively simple if you just use your tables and your equations and you just fill it in.